All right, textbooks open to page 109. We've been doing a lot of trigonometry lately, a lot of SOHCAHTOA, right, Kendall? Yeah, so getting some practice with those things. And your homework last night was to do the challenge problem on page 109, problem number 12. Go ahead and read the problem if you would, Audrey, and we'll see who was up to the challenge.
Challenge problem. 3 forces pull on an object. 50 newtons at 0 degrees, 70 newtons at 70 degrees, and 60 newtons at 230 degrees. What is the resultant? Use the component method explained in section 7.6.
All right, so we start with the Cartesian plane. We have, and I'll use white to show this here. Right at 0 degrees, we have a 50 Newton force. It says at 70 degrees, we have a 70 Newton force. And at 230 degrees, well, hold on, this would be 90, 180. We have to go 50 more degrees down here. So something like this, we have a 60 Newton force. Now, Kendall, I'm not sure how familiar, I guess we talked about reflex angles in geometry, so you're familiar with 230 degrees being past the right angle, or past the straight angle, so that's what we've got going on here, and a lot of angles. So 70 degrees here, and while this whole angle's 230, that's kind of awkward to use, isn't it? It might be easier if instead we just think of this angle class as being 50 degrees. Because after all, it's 50 degrees beyond the 180. All right, and then we want to take the component method. So I'm going to call these force 1, force 2, and force 3. And each one we're going to split into x and y components. X being horizontal, y being vertical. Now, the first force, force 1, should be really easy to split into components. What is the x component of the 50 newtons class? 50 newtons. And what is the y component of the 50 newtons class? 0 newtons. I trust we did fine on the first force. A little bit of a challenge comes from the second force because some of this force goes up and some of this force goes forward in the x, right? And so we need to figure out how much of it is x, how much of it is y. Well, the 70, of course, is right here. And in our, what shape class?
Triangle.
Right triangle. The 70 is the hypotenuse. So the hypotenuse is the 70. The x would be considered, with relative to this 70 degree angle class, the x is the adjacent. And the y is the opposite. So if I wanted to find the x component, I would need the adjacent, but I know the hypotenuse. SOHCAHTOA, adjacent hypotenuse. Which trig ratio, Kendall?
Cosine.
Cosine. We know that cosine is adjacent over hypotenuse. So we'll say that the cosine of the angle, in this case a 70 degree angle, is equal to the adjacent, well, I don't know it, it's whatever that force is in the x, right? Over the hypotenuse, which we know is 70 newtons. Put the cosine over 1, we'll cross multiply the cosine of 70 times the 70 newtons. And Kendall, what did you get for the x component of force 2?
23.941.
Good, 23.94 blah, blah, blah newtons. That's going into memory 1. And then for the opposite, this y here, well, again, I'm needing the opposite. I know the hypotenuse. SOHCAHTOA, Michael?
Sine.
Sine. Because we know sine is opposite over hypotenuse. So we'll say that the sine of
70 degrees.
is equal to the opposite,
X, or Y.
y in this case, over the hypotenuse, 70 newtons. And so we'll take the 70 newtons, we'll multiply by the sine of 70. And how many newtons go upward in the y?
65.778.
And I'll go ahead and put that in memory 2. Then we come to our final one, and there's a couple ways you could do this one. We realize that the y goes downward negatively. we realize that the x is going backward negatively. So when we get our x and when we get our y, we're going to need to put a negative on both of them. Does that make sense? If you use 50. Now, if you used the 230 ASTC, sine and cosine are both going to come out negative already. So if we just use the 230-degree angle, you're already going to get the negatives. If you go off the 50-degree angle, which makes a little bit more sense for a right triangle, we're going to have to put a negative on whatever we get for x and put a negative on whatever we get for y. Does that make sense? Okay, so kind of talking to two groups here. All right, so for the x, what trig ratio are we going to need to use here? Audrey? Cosine. We'll take the cosine of, I'm going to go with what we've got drawn here. I'm going to say the cosine of 50-degree angle. You realize you could use 230. And then we're going to say that's the adjacent x over the hypotenuse 60. And so for our third force, what do we get for the x vector, x component? Re-entering.
38.567.
Good, 38 if you use 50 degrees. But we have to make it negative because it's going backward, right? If you use 230, you would already have the negative sitting there waiting for you. So negative 38.567, blah, 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 newtons. We're going to go ahead and put this in memory 3. And then finally for the y, Kendall, we're going to use what trig ratio?
Sine.
Sine. Opposite hypotenuse, we use the sine, so we'll say that the sine of 50 equals the opposite y over the hypotenuse 60. And we multiply, and what do we get, Kendall?
Negative 45.162.
And I don't have a memory left for that one, so I'm going to keep it on my calculator screen. Check your components. How many went 6 for 6 on components? Everyone's good. Outstanding. So now what we need to do is find the sum of all the x's. Well, I don't want to do that first, because what's on my calculator is a y, correct? I'm going to go with the sum of the forces in the y first. So on my calculator right now, I have a negative 45.96. I'm going to add this negative that runs downward to this positive that runs upward, and we would add the 0, but there's nothing to add, right? So I'm going to take is what's on my calculator plus the memory 2, or plus recall 2. What is the sum or the resultant up and down, class?
19.815.
A positive 19.815, blah, blah, blah. So because it's positive, it means the resultant y is up. There is more up than there is down. Does that make sense? So resultant of y is up. How many had the 19.81 blah, blah, blah newtons? And I'm going to put that in memory 2. I'm going to overwrite the old memory. All right, we all get that? Excellent. For the x's, I've got 50 going forward, I've got 23 going forward, but then I've got 45 or 38 going backward. I've already made it a negative, so literally I just add 50 plus blah, 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 plus the negative. If I hadn't made it a negative, I'd have to subtract it. I made it a negative, so I wouldn't have to think about it. So we're going to take 50 plus recall 1 plus recall 3. And what is the resultant horizontally here? Audrey? 35.37, all good with that. And I'm going to overwrite memory 1 there. Store 1. And that's going forward because it's positive. Now, the question is though, how do I then come full circle and find what really happened? All this stuff going down, what really happened, how do I finish it out? Kendall? Or is this as far as you got, was the x and the y sums? Michael?
To make a triangle.
Good. You take this one vector, and you take this one perpendicular, and you make a single right triangle out of the two sort of resultants. And so let me give myself a little space, but I do want to leave the original picture. So, right over just a notch. Okay. So we got a forward 35, we have an upward 19. Which one should I draw first as the primary vector class?
35.
Whichever one's bigger, so the 35. So I'm going to start horizontal at 35.37, blah, blah, blah. Then I'm going to go up 19.81, blah, blah, blah. And the actual resultant is going to be right around here somewhere. So we've got a force pushing this way, we've got a force pushing that way, we've got a force pulling that way. The resultant is probably going to be something like that when it's all said and done. That's going to be the outcome of all those forces. All right, well, how do I find the magnitude of the resultant, class? Pythagorean theorem. I've got memory values for both of these, so I can do a recall 1 squared plus recall 2 squared equals take the square root. What is the magnitude? We've got a 40 Newton force, a 70 Newton force, a 60 Newton force kind of pulling back. What's the resultant force?
40.546.
40.54 blah, blah, blah newtons, or I think it's 2 sig figs here, yes, so we'll say approximately 41 newtons when it's all said and done. You two good on that? Okay, and then you're seeing it now, okay? But I also need to know the angle, right? Because there was a head-on, there was a 70-degree angle off, there was a 50-degree angle back, or 230-degree angle. What's the actual angle going to wind up being? Well, to find the angle, Kendall, I need to use the arctangent, because I was given the opposite, the adjacent. So you say, well, I know the hypotenuse now. Yeah, but that's a calculation of a calculation of a calculation. At least these are just calculations of calculations. I mean, you're doomed to use calculated values either way, but these are less calculated by one step. So let's take the opposite, which was in memory 2, divided by the adjacent, which was memory 1, and we're going to take the arctangent of the O over A, and when we do, we end up getting what angle, anyone?
29.25.
29.25, blah, 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 or we'll say rounded
20.
29 degrees. Questions on this? What if, humor me here, what if one of the forces had done this and one of the forces had done that? And I got a 29-degree angle. Would I say that the angle was 29 degrees? No, because then it would be a 29-degree angle here. But what's the actual angle? What would I have to do?
189.
I'd have to subtract the 29 off the 180 to get, 151? Or what if it had been this way and then downward, and we found a 29-degree angle? Well, I wouldn't say it was 29 degrees. I'd say it was 180 plus the 29 would give me 209. Or what if it had been over, but it went down, and I found the angle is 29 degrees? Well, I wouldn't say it was 29, I'd say it was just shy of 360, right? 29 shy, so what is that, 331? Okay, so you'd have to gauge the angle relative to the positioning, but in this case, yeah, it worked out great because we were coming right off the x-axis anyway, 29 degrees. Questions on the challenge problem? So you both nailed it, and you were right there, you just needed to make the right triangle at the end. Outstanding job. Questions at all on that? All right, let's do another problem here, and we can use the Cartesian plane, I suppose, as reference. I'm going to go north, south, east, west, though, so not so much x and y Cartesian plane as much as kind of a north, south, east, west compass style thing. And I like football, so we're going to do a football problem, okay? And let's suppose we've got a particular football field that aims one end zone due north, the other end zone due south. Okay, for instance, the Patriots end zone might be due south and the Colts end zone due north in glory. Anyway, wait, they're dying? Anyway, that illustration. Okay, but anyway, we've got a football field that runs due north and south. Okay, so here is football field, north, south, end zones, north end zone. And the running back is going due north, so we'll go RB for running back. He's running due north, which, by the way, is always good to run forward, right? Sometimes frustrated watching the running backs like trying to find a spot. Just go forward somewhere already. Get something. So losing yards. Anyway, he's going forward and he slows down momentarily. Like running backs at their top speed can be 22, 23 miles an hour. But he has to slow down momentarily, trying to juke a defender. And when he slows down, he's right about, let's see, he's going about 12 miles an hour preparing his shifty move. But in that moment, he slows down to about 12 miles an hour. That gives the defenders a chance to catch up to him. We've got a linebacker, and let's, for sake of consistency, say that these two athletes have the exact same mass. That's going to be important because if they don't, the problem doesn't work. So we'll say we've got a 220-pound running back, which is slightly on the small side, but not much. That's pretty good. And we got a 220-pound linebacker. He might be a little undersized, but he's really fast, okay? So he comes up behind him, but not directly behind him, collinear. He comes behind, he's going 32 degrees to the west of north. All right, so the running back's going downfield like this, but the linebacker hits him. He's going 32 degrees to the west of north. So the linebacker's not going north. He's coming in a little bit, 32 degrees to make this tackle. That make sense? So he's tackling him from behind, but it's behind at an angle. And he's running, when he crashes into him to make the tackle, he's going 14 miles per hour, which is why he's able to catch up to him. He's running faster, so of course he's able to catch up and make that tackle. At the exact same moment, a well-meaning safety comes along. Okay? And this is a big safety if he's 220 pounds. They're not usually that big, but he's a big safety. He's a box safety. His job is to tackle running backs. And he comes at him, and he's going this way, but down. So he kind of makes a little bit more of a head-on collision. Not going east, but coming south of east to make the tackle, because the safety plays deeper. So the linebacker comes up behind him. The safety's coming down on him. Let's suppose the safety makes an angle of 18 degrees to the south of east. So kind of a sideways tackle, coming down a little bit in his face. Safety's a little bit quicker. He's going 15 miles per hour. There's a big boom, not a big bang. We don't believe in that. A big boom, and when the dust settles and the smoke clears, there's 3 guys laying on the ground with concussions, and no one knows where the football went. Probably somebody let the air out. That's what happened. Anyway, picking on Patriot fan over there now. Anyway, the question is, what's the resultant of the collision? In that brief moment before they all crash to the ground, the group somehow, some way, running back at least, goes somewhere with some velocity right before he crashes to the ground. What is the resultant velocity? You're going to want to take the running back, go X and Y, linebacker, go X and Y, safety, go X and Y, and then put all the components back together for one final resultant. So a lot like the challenge problem, except we're using north, south, east, west. At your seats. Give you a few minutes to get a head start, then I will begin working it at the board so you can kind of check and see if you're on the right track. And Kendall's like, it's not who let the air out, it's who let the dogs out, Mr. Datsky. Come on, you're in Georgia. Wait, you're a Gator fan anyway. You're not a Georgia fan, right?
No, I hate Georgia.
Yeah, sorry, my bad. Chomp chomp. And Michael, you're football, not football.
Yeah.
So you don't even care. So Michael, the ball is rolling forward, you have a slide tackle from the side, and you have a kick from behind, all happening at the once. What happens to the ball? Yes, somehow they all it's a bad illustration because they don't have equal masses. I tried. Let's stick to good old American football. right, check your components. Obviously, the running back, 0x positive 12y, right? And no issues with the running back, correct? Okay, with the linebacker, he's going north and west at the same time. West is your x. I have him going backward or negative 7.41. Again, you don't have to think of it as negative, but you have to remember it's going this way. And still going northward, just like the running back at 11.87. Did we get those two components? And then for the safety coming down to make the tackle, I have him going opposite the direction of the linebacker. So he's going forward, so I call that positive. You could just think of it as east. Just realize they're going opposite directions. 14.26 as he makes the tackle from the side. A little bit of downhill up opposite the direction of the running back at 4.635. Did we get those two components? Any questions on those components? All right, continue from there. Just want to make sure if the components are wrong, fix the components and proceed. If you're good, continue on with what you're doing. Do we get these two resultants? The resultant is you're going 6 this way and 19 that way. Again, just for a brief moment before crashing to the ground. Questions on the sums in the x and the sums in the y. All right, so when we go to figure out the running back's momentary resultant velocity, which is the primary vector? The 19, the going forward. Again, he was only going 12 miles an hour. Being hit from behind like that really sped him up. Again, just for a moment. He's going to hit the ground anyway in a second. But it did speed him up to 19.237 going north toward the end zone. It also pushed him off course toward the sideline, this direction, 6.846. And I should probably write the 19.237 off to this side so I can draw the resultant. How do I find the magnitude of the resultant, class? Pythagorean theorem. And we should, somebody, right? Let's try that again. Recall 1 squared plus recall 2 squared equals square root. There we go. How fast does the running back go for just a brief moment, class? 20.419. Now, by the way, think about it. He was only going 12. All of a sudden, he gets hit, and he's going forward 20.419. You understand where whiplash injuries come from? The head is still wanting to go 12, and the body suddenly starts going 20.419 upon being hit. Whiplash, okay? Neck injuries, concussions, bad things in the NFL. All right, we'll round it off, and we'll say about 20 miles per hour. And then he's pushed at an angle. He was going straight down the field. He got a little bit of a sideways whiplash here, though, because he got pushed off course. To find the angle, we use the arctangent. So we're going to take, let's see, that's recall 1 divided by recall 2. Take the arctangent. What's the angle, class? Hey, that worked out great. And 19.59, blah, 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 at 20 degrees. And he was going north, but he got pushed by the safety, really, to the east of north. 2020. There's our answer. 20 miles an hour at 20 degrees east of north. Did anyone get all the way to the end? Good, Audrey. Michael Kendall, questions. How close did we get to the end?
I was almost finished. I was on the right track.
Okay, you just didn't have time to finish. I cut it a little too soon.
I screwed it up when I set it up.
So components were wrong to begin with.
No, they were right, but when I heard you say set up Cartesian plane, that's how I did everything, and that messed up my angles.
I got you. Yeah, so if I went with the Cartesian plane approach, and I set it, and then I suddenly went with a football field drawing instead, I'd have the running back doing this. I would have the safety doing west of north, or the linebacker doing that, and I would have the safety doing that. And that's how we draw it. So we'd have a 32 here, we'd have a 0 degree angle there, and there's the 18. So it should have still worked out with the same X and Y components.
It did, it just, the directions got messed up.
Gotcha. Okay. All right. Questions at all? All right. Well, let's go ahead and kind of look at a scenario that was mentioned in your textbook. The first problem on a work, though, is something we've been doing for a while, right? We've worked problems where boy stands on bridge and drops rock, man stands at the top of Empire State Building, drops penny, okay, whatever. Let's suppose we've got a guy at the top of a 5-story building, and, you know, it was really popular a year or two ago, if you were in a big city, to throw bricks and stuff. So there were bricks, pallets of bricks strategically placed for groups in case they randomly decided they needed to build a building or break windows. And so anyway, let's suppose there's a random brick that managed to land up on the top of the building. And from the top of this 5-story building, which we'll say is 12.5 meters high, a guy's like, I wonder if this brick will break if I drop it. And so he holds it out over the edge. He doesn't notice Kendall standing down there. Just kidding. He doesn't see somebody standing there, but he checks for safety, because we recommend safety here at Grace Christian School. Nobody's standing down there. Make sure nobody's going to come anytime soon. And he drops the brick. Well, there's a few things we know about this scenario. What do we know? Gravity's going to pull that brick down, isn't it? At what rate? Meters per second squared. So class, we know the acceleration of the brick. What else do we know about the brick?
Its initial velocity
Is?
0.
0 meters per second, right? Because it just dropped the brick. What else do we know about the brick? We don't, well, once it hits the ground and busts into pieces, right? I mean, the pieces will eventually come to rest, but how about the split second before it hits the ground? That's its maximum velocity. We actually don't know the final velocity, but I'd be interested to find out. But what else do we know? The displacement of the brick. Now, again, this kind of assumes he's holding the brick right at building level. It might have held it a little higher, but let's just assume it's right at building level, drops the brick, or maybe just pushes the brick off right to the edge, and then just tiniest little, and then it falls down. All right, so the displacement of the brick is the 12.5 meters. I don't know how fast it's going to go the split second before it hits the ground, nor do I know how long it'll take to hit the ground. I don't know the time, but I can find both of these. I would recommend finding final velocity first. Which equation would we have needed to use, going back to pre-exam, what equation would I need to use to find the final velocity?
Vf squared plus 2ab.
Absolutely. Vf squared equals vi squared plus 2ab, where since I'm solving for v sub f, I don't even have to manipulate anything. I just need to take the square root. Conveniently, the v sub I is 0, isn't it? So really, all I'm doing is taking the square root of 2ad, so I shouldn't have much opportunity to screw this up, which is nice. I like not being able to screw things up. And don't forget to take the square root. That would screw things up. How fast is that brick going to be going right before it goes splinter and shatter and bust?
15.65.
It'll be going 15.65, blah, blah, blah. I'm going to suggest we put this number in the memory of our calculator. We're going to want it later. Now, if we were rounding off to sig figs, we'd say, well, that's approximately 15.7 meters per second, but we'll keep that number in the memory of the calculator. If I put it in the memory, I can use it again. Again, as long as I'm confident I didn't screw anything up, but you realize we're kind of to the point now where we just got to kind of bank on ourselves, bet on ourselves that we're not going to screw things up. So when I go to find the time, if we allow ourselves to use the v sub f, there's a number of ways I could find time. What's an equation that would include time? The acceleration equation, where I'd have to alternate to get time by itself. So t would equal there we go. It is change in velocity over time, but time is change in velocity over acceleration. We know the final velocity. It's actually still in the calculator, even if I didn't have the memory. The initial velocity is 0 anyway, so I really just take what I've got divided by acceleration. And again, assuming a vacuum, which again, terminal velocity, I don't think it would hit. It wouldn't slow it down much. It's a brick, right? So probably still hitting that 15.7 meters per second. The time would be about
1.6 seconds.
Yeah, about 1.6 seconds, 1.597. Go and put that in memory too, in case we need that number here in a moment. But we're going to round it off and say 1.60 seconds when we go to the third sig fig. All of this we've done before. No difference. But what if, instead of just dropping something off, or instead of throwing something straight up, or throwing something straight down, what if something were thrown perfectly horizontal? For instance, what if from this same height, instead of nudging a brick off the edge, somebody chucks a baseball perfectly horizontal? What's going to happen to the baseball? It's going to go down, but it wasn't thrown down. Why does it go down anyway? Because of gravity. But it doesn't go straight down either. What does it do? It keeps going forward and going down, and forward and going down. Do you see there's two different components of motion? So now let's take a baseball. Baseball, it helped if I could spell. And let's suppose it's thrown horizontally at 37 meters per second. So about a 75-mile-an-hour throw. Okay, so this is, high school player probably, not big leaguer by any stretch. But a baseball player throws the ball horizontally off the top of the building. Now again, we're going to ignore the height of the baseball player, so we'll say the ball starts out still 12.5 meters up. But there's two separate components to its motion. We have the x, we have the y. Here, class, everything was y. All the motion was vertical. We could say the displacement of the y was this, acceleration of the y was this, initial velocity of the y was this, final velocity of the y was this. Time? Time's a scalar, right? It doesn't have direction or component, so time is still just the 1.597, whatever. So let's think about our baseball. Well, we still know if it's thrown from a height of 12.5 meters, eventually it has got to drop a total of 12.5 meters, right? The displacement in the y is still 12.5 meters. How far this way will it go? I don't know. Let's find it. Let's find the displacement in the x here in just a minute. Does that make sense? I also know if it's thrown perfectly horizontal, is there any motion forcing it down right as it's released? No. But all 37 meters per second is going forward, correct? So I know that in the x, the initial velocity is 37 meters per second. But the initial velocity in the y is still 0 meters per second, if it's perfectly horizontal, correct? Now think about it. What about the final velocity? Well, it's going to have a final velocity in the y. It's going to have a final velocity in the x as well. Now remember, we're ignoring air resistance. If there's no air resistance, what will slow the ball down in its forward flight? Nothing, unless it hits something, right? That would stop its forward flight, right? But assuming there's wide open spaces, that ball's just going to keep going 37 if nothing slows it down. Is there anything to speed the ball up? No, once it leaves the hand, there's nothing to propel it forward, right? It's not like a missile or something that continues to propel itself. So if there's no air resistance to slow it down and there's nothing that can speed it up, what will the horizontal final velocity be?
37.
Still 37 meters per second. Does that make sense? Which means, by the way, that the average velocity in the x, the horizontal movement, will be 37 meters per second, right? If the initial and the final are both 37 and the average is 37, we could say. Not going to be the case for the y, though, because in the y, it does speed up, correct? It starts off out of the hand going horizontal, but little by little it begins to drop faster and faster, doesn't it? Why? Because of gravity. So there's an acceleration in the y of 9.80 meters per second squared, while in the x, there is no acceleration. Does that make sense? The y has acceleration, the x has nothing, if we're ignoring air resistance. Well, we've got initial, final, displacement, acceleration. All we're missing here is time. And we're missing time from both columns, correct? But notice something. Does the x in any way affect the y? If there's air resistance, technically yes. But if there's no air resistance, the x in no way affects the y. If this is in a vacuum, forward motion doesn't do a thing to vertical drop. After all, if in the last problem we had a displacement of 12.5 meters, if in the last problem we had an acceleration of 9.80 meters per second squared, in the last problem it started out vertically at nothing, then by the end it was at a drop rate of 15.7 meters per second. Do you realize that vertically, right before it hits the ground somewhere over there, vertically, it'll be going 15.65 meters per second? And that's still in memory 1. That make sense? You could do the same equation over again, but you'd still get the same answer, wouldn't you? Now here's another thought for you. If it's dropping at the same rate, and it starts its fall at the same rate, and it has to drop the same distance as that brick, do you realize? No air resistance, remember. It's going to take the same amount of time to hit the ground. The difference is the brick hits the ground right there. The ball hits the ground somewhere over there, but it's still, if there's no air resistance, going to hit the ground at the exact same time. The time of fall is still going to be the 1.597 blah, blah, blah seconds that's in memory 2. Does that make sense? So here's the question. The y is easily solvable because we just solved it for a brick. How do I then come over to the x? There's one thing that can bridge the gap. Acceleration in the y does not have any effect on acceleration in the x. Initial in the y has no effect on initial in the x. Final in the y has no effect on final in the x. Displacement of the y has no effect on displacement of the x. But time bridges the gap. Do you see that? Because time's a scalar. All it has is magnitude. If it drops for 1.597 blah, blah, blah seconds, how long does it fly forward? 1.597 blah, blah, blah seconds, because that's how long it's in the air. Once it hits the ground, it's done with its flight. So as long as it stays in the air vertically is how long it continues to go forward horizontally as well. Write this in your notes. Use the y component to find time. You will always, with objects flying through the air, you will always use the y component to find time. Always use the y component to find time. what we have. I need the displacement in the x. I already know the initial, the final, the average, the time, the acceleration. The only thing I don't know in the x is how far does it go. From the top of the building, well, rather from the base of the building, from that point to where it finally crashes this point, how far is that? Does that make sense? Technically, it would be how far from the base of the building does it land. Does that make sense? What is, not the actual distance traveled through the air, but how far from the base of the building does it land? That displacement of the x. Well, if I know average velocity and I know time, looking over there, average velocity, time, if I just multiply, I get displacement, right? Looking at the one right next to the guy's shirt. So take the time, it's memory 2 in your calculator, multiply it by the 37 average in the x, which is also initial, which is also final. How far does this ball go?
59 meters.
Yeah, 59.09 blah, 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 or pretty much 59 meters. Which, what is that, about 62, 63 yards? That's 180, 190 feet-ish, plus or minus-ish. That's a halfway decent throw for a high school baseball player. That's not too bad. Do you see how we can use y to get x? And it goes through time. That's the only thing that they share. But here's another question. When the ball hits the ground, how fast is it going? Well, remember, horizontally, class, it's still going the 37, because there was nothing to slow it down if we're ignoring air resistance, but it also has a vertical movement now. When it left his hand, it didn't have a vertical movement, did it? He left his hand at actually 37, but gravity's been speeding it up a little bit. It is now, right before impact, it's going 15.65 meters per second, isn't it? So the question is, when it hits the ground, how fast is it actually going? And we can now use x and y together to get that resultant velocity. Not that it's sped up much, but it technically lands faster than it left his hand. How fast was it going when it hit the ground, class?
40.17.
40.17, blah, 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 or approximately 40 meters per second on impact. Good to go there? But does the ball hit the ground straight down, like the brick? No, it's going to come in kind of at an angle, isn't it? Right? Because we know the flight, it's going to go forward, and then it's going to go down a little bit, and then forward and down a little more, forward, down a little more, right? Because it keeps going faster and faster downward. So what ends up happening is we get a little bit of this curved drop. The question is, at what angle would it hit the ground? Well, this angle of elevation, Michael, would be the same as the angle of depression, or kind of alternate interior angles equal, right? So I can find this angle between the vector and the resultant, and that'll be the angle at which it actually hits the ground. Again, if we ignored air resistance. So let's go and do that now. Recall 1 divided by 37, take the arc tangent. What angle does it hit the ground? 22.93 or 23 degrees to the ground. And now we can start doing calculations, still using those formulas, but now looking at two different components, two vertical components, that the one does not affect the other, but they can work in tandem to get a velocity as well. Questions on that? So what we have here then, this baseball, even the brick, anything that goes into the air and can't continue to propel itself, it just, once it's in the air, it does whatever it does. This is called a projectile. If you write that term in your notes, projectile. Projectile is any object that is launched or hurled through space. Any object that is launched or hurled through space and can no longer propel itself. Any object that is launched or hurled through space but lacks the ability to propel itself. Any object launched or hurled through space that cannot continue to propel itself is a projectile. And we talked about this the other day as we went over the homework, right? Some different examples of projectiles. The path that a projectile will follow is called its trajectory. Trajectory. Sometimes we use this to talk about students and, how are they doing in their classes? Are their grades coming up? Are their grades coming down? What path do we see their grades following? I actually used that last night talking to a parent. Well, if we take the trajectory I'm expecting, and then the physics teacher in me is like, what, are we launching the kid? No, we're not launching the kid, just the grades. The grades are going to launch. Anyway, trajectory is the path of a projectile. The path of a projectile. But here's what you need to know about the trajectory. Because of the way we have the squared drop with acceleration to the linear forward motion in a vacuum, we will get a perfect half parabola. Remember from algebra 2, over 1 down 1, over 1 down 3, over 1 down 5, and so forth? Right, we get that more rapid drop. We'll get a parabolic drop. If you throw something up into the air, what you're going to get is you're going to get rise, and then the rise will get less and less and less as the forward movement continues on. So you'll actually get a parabolic trajectory. So you need to know that the trajectory of a projectile will be parabolic if there's no air resistance. If there's no air resistance, we have a parabolic trajectory. Now, with air resistance, and the book mentions this, instead of a nice parabolic trajectory, what we'll end up with is it'll land a little sooner than it should. It'll kind of round off that back end. It'll start off fine, and then little by little, as air resistance has longer and longer to affect it, it'll shorten up that distance. But remember, we live in the perfect world of physics where we ignore air resistance for all of our math problems. So for our purposes, we will have parabolic trajectories. We'll look at more projectiles in the next couple of lessons. For tonight, though, no homework. And when the bell rings, you are dismissed. Have a wonderful rest of your day.